This is part 2 of the chapter 32 video. I incorrectly wrote chapter 22. This is chapter 32. And this is the remainder estimate for the integral test. And the remainder estimate for the integral test is based on the same principle as the proof of the integral test. So here we're just going to pick some number k, and we're going to look at our series from n equal k plus 1 to infinity of xn. So we're not going to worry about the first k terms. We're just going to look at from k plus 1 on. And so when we do that, when we take the right endpoint as our function value here, then this rectangle has height k plus 1 and has width 1. So it has area k plus 1. This has height x sub k plus 2 and width 1. So it has area x sub k plus 2. And so when we look at this, we see that the sum n equal k plus 1 to infinity of x sub n is less than or equal to the improper integral when we integrate from k to infinity of f of x. And then just like we did with the proof of the integral test, we take our picture and we label it a little bit differently. Now we look at the left end points for the function values. So now we have f of k plus 1 is x sub k plus 1. That's the height of this rectangle. The width is 1, so the area is x sub k plus 1. Area of this rectangle is x sub k plus 2. And then when we sum n equal k plus 1 to infinity of x sub n, that's greater than or equal to the improper integral from k plus 1 to infinity of f of x dx. So now what these two things tell us is that we have an upper bound and a lower bound for the sum from k plus 1 to infinity. This gives us an inequality. So the integral from k plus 1 to infinity of f of x dx is less than or equal to the sum of n equal k plus 1 to infinity of x sub n, which is less than or equal to the integral from k to infinity of f of x dx. And this is the tail end of our series that we're interested in. And so what that means is, if we look at the sum of the first k terms, the sum n equal 1 to k of x sub n plus the integral k plus 1 to infinity of f of x dx, that's less than or equal to the sum n equal 1 to infinity of x sub n, because we've taken the tail and then we've also added n equal 1 to k of this sum. That is less than or equal to the sum of n equal 1 to k of x sub n plus the integral from k to infinity of f of x dx. So the sum that we have that we're interested in is in between this sum plus this integral and the same sum plus this other improper integral. The reason we're interested in this is here we're just adding a finite set of numbers. We can do that. We're calculating an improper integral here. The same finite set of numbers we're adding here, and then we calculate another improper integral. This gives us a bound for our series. And then we can subtract this sum all the way through. And when we do that, we have the integral k plus 1 to infinity f of x dx less than or equal to the sum n equal 1 to infinity of x sub n minus the sum n equal 1 to k of x sub n less than or equal to the integral k to infinity of f of x dx. This is our estimate. So we've taken a finite sum and we're calling this the estimate of this sum. We know that it's going to be a little bit smaller than this sum. So the true sum that we want minus our estimate, we know that this is our error. And it is between this number and this number. For a large enough k, if we can make this small and this small, then we've come up with a very good estimate for our sum. And that's what we're going to do in example 209. So for example 209, we're looking at the sum n equal 1 to infinity of 1 divided by n squared. I told you in another video that this sum to pi squared over 6. I'm not going to quite prove that this sum is pi squared over 6. What I am going to do is I'm going to use theorem 207 to show you that pi squared over 6 is a very, very, very good guess. So, we're going to let our k be 999. So we're going to do three things at first. We're going to integrate 999 to infinity of 1 over x squared dx. I will explain why I chose 999 in a minute. This is the limit as t tends to infinity of the integral from 999 to t of 1 over x squared dx, which is the limit as t goes to infinity of negative 1 divided by x evaluated at 999 and t, which is the limit as t goes to infinity of negative 1 over t minus negative 1 divided by 999. This term goes to 0, so we have 1 divided by 999. The integral from 1000 to infinity of 1 over x squared dx, if you look at these steps here, what is the difference? We have 1 over 1000 instead of 1 over 999, so this integral is 1 divided by 1000. The rest of these things are TI 83 plus calculations. So TI 83 plus these are the calculations that I get from a TI 83 plus. The sum of n equal 1 to 999 of 1 divided by n squared. This is the reason I chose 999, is it was the highest number that my TI 83 plus would calculate. This is 1.6 439 33567. 6, 4, 3, 9, 3, 3, 5, 6, 7. The sum of n equal 1 to 999 of 1 over n squared plus 1 divided by 1,000 is 1.64493567. We're adding 1,000, so all we did is increase this digit by 1. The sum of n equal 1 to 999 of 1 over n squared plus 1 divided by 199 is 1.644 934 568. And according to my 83 plus, pi squared over 6 is approximately 1.644934067. So we've summed to 999, and we know the true sum is somewhere between this number. Let's see. So this is our estimate, and so we know the true sum is somewhere between this number and this number. And pi squared over 6, if it is not the actual sum, it is a very, very good guess.